Welcome to The Explainer. Today, we're tackling one of the absolute most fascinating challenges in modern engineering and tech. Think about it. How do we effectively monitor, predict, and optimize really complex real-world systems? Whether we're talking about a cathedral-sized power station or an entire global supply chain, managing those massive physical assets is, well, incredibly difficult. But there's a game-changing solution that is literally reshaping how we interact with the physical world: the digital twin. We're going to break down exactly what this technology is, how it actually works, and most importantly, how you can build one yourself.
To really set the stage here, I was looking at this super relatable question from a developer over on the r/IoT Reddit community. They basically asked, how do I map real-time sensor data to 3D model parts? They already had the 3D models built in Blender, they had the IoT sensors on the desk, but connecting them into a dynamic living system, that is a massive technical hurdle. It's a fantastic question, and it perfectly captures the human problem-solving journey we're going on today. Because by the end of this, we're going to answer that exact dilemma.
Okay, so let's just dive right in. Here's our roadmap. 1. Defining the digital twin. 2. The operational platform. 3. Simulation engines. 4. Visualizing data. And 5. Real-world applications.
All right, part 1, defining the digital twin and separating fact from fiction.
So the foundational concept here actually comes from Michael Greaves. And for a true digital twin, you absolutely need 3 specific things. You need the physical object itself, the virtual object, and this is the crucial part, the continuous automatic data connecting them in both directions. Without that bidirectional flow, you don't really have a twin. You basically just have a very expensive picture.
Breaking it down like this brilliantly illustrates the difference. Say you have a standard 3D CAD drawing where you have to move data manually. That's just a digital model. Now, if you have automatic sensor data flowing from the physical object to the digital object, but it doesn't go the other way around, that's what we call a digital shadow. The main takeaway here is that only when you achieve automatic two-way data flow do you actually have a true digital twin.
Moving right along to part 2, building the operational platform. Let's look at the DTOP architecture.
A really fantastic blueprint for moving from theory to practice is the open-source DTOP-Cristallo project developed by the University of Liverpool. A browser-based digital twin operational platform, or DTOP, relies on 3 core layers. First up, the IoT layer, which is your physical sensors and actuators. Second, the interface layer, which is typically a web server that routes everything. And third, the cloud computing layer for all that massive data storage and high-performance computing.
Now, when you're actually building this platform, you've got to choose your accessibility format. And it's a bit of a trade-off. On one hand, you have a standalone system running on a local machine. This gives you maximum data security, which, as you can imagine, is absolutely vital for things like military infrastructure or high-security energy grids. On the flip side, you have a web-based platform using tools like Python and Flask. That trades a little bit of local security for incredible flexibility, letting you have global, collaborative access from virtually any device.
Okay, part 3, powering the simulation engine. This is really the brains of the operation.
The specific open-source stack used in robust systems like DTOP-Cristallo is just so cool to look at under the hood. Python and Flask handle all the core routing. PostgreSQL integrated through Salkami is absolutely perfect for storing huge arrays of sensor data. Then you've got the Redis server, an in-memory data cache doing the heavy lifting of managing server queues and distributing simulation tasks across multiple machines. And finally, libraries like NumPy and Pandas step in to scrub and process those massive incoming datasets.
And the sheer processing power of these engines, it is staggering. By utilizing advanced techniques like the reduced basis finite element analysis that MIT developed and Exelos commercialized, digital twins can simulate the physics of massive energy infrastructures up to 1,000 times faster than older conventional methods. To put that into perspective, that's the kind of speed you need to make near real-time prediction and asset management actually possible.
But hey, you don't always have to write the complex math from scratch. Actually, scratch that. You rarely do. Python scripts running inside your twin can automatically trigger trusted commercial third-party software like ABAQUS or MATLAB to just run complex structural analyses quietly in the background. In the DTOP-Cristallo project, for example, they use this exact method to test the natural frequencies of a 3-story physical structure and then funnel the results right back to the user's dashboard automatically.
Which brings us to part 4, visualizing real-time data and bringing the twin to life.
So to finally answer our Reddit developer's dilemma from earlier, industry experts suggest breaking this seemingly impossible task down into manageable parts using a specific tech stack. First, you build your static models in software like Blender or Autodesk Fusion 360. Next, you use communication protocols like MQTT or WebSockets to stream your live data. And finally, you throw it into a powerful visualization engine like Unity or specialized simulation software like Simio to map that data directly to the model. That's how things change color or state dynamically as the data flows in.
And this brilliantly illustrates how combining these tools creates an incredibly effective synergy. Take the integration of Python and Simio, for instance. Python is acting as the brains here. It's cleaning up the raw, noisy sensor data and running the heavy machine learning algorithms. It then feeds that squeaky clean intelligence over to Simio, which handles the object-oriented 3D animation and discrete event simulation. Put them together, and they create these highly adaptive, near real-time models that essentially adjust themselves autonomously.
All right, final section, part 5, real-world applications. Digital twins in action.
Because this isn't just theory, right? Digital twins are solving massive, real-world problems today. In healthcare, hospitals use them to simulate emergency room patient flows based on historical patterns so they can optimize their staffing. Over in the energy sector, companies like Axelos are building twins of cathedral-sized hydroelectric power stations and offshore wind turbines to predict maintenance needs based on real-time weather data. And in manufacturing, companies are using platforms like Simio to test intricate assembly line tweaks completely virtually before they commit a single dollar on the actual factory floor.
And the financial impact of all this tech is huge. By using these dynamic digital twins for virtual validation and manufacturing, companies are slashing physical implementation costs by 15 to 30%. Think about that. They are identifying bottlenecks and testing solutions completely in the digital realm, which means they are avoiding costly physical downtime entirely.
So the next time you look at a complex physical system, whether that's a sprawling assembly line, a massive skyscraper, or even just your local traffic grid, don't just see the steel and concrete. I want you to see the data. Think about the physical, the digital, and the automatic link running between them. I'll leave you with this final thought. What complex system in your own life or industry could be completely transformed by building its own digital twin? Thank you so much for joining me for this explainer, and keep exploring.